Our speaker this week is Giuseppe Romana, who is in Helsinki right now, and he's going to speak to us about string attractors from data compression to combinatorics on words.
Thank you very much for the introduction. So yeah, I'm Giuseppe Romana. I'm a PhD student. I'm currently in Helsinki, but actually I'm from the University of Palermo. And just to give you an outline of the talk, first I will introduce the notion of string attractor, and which was defined in the data compression field. Then I will present some combinatorial results on finite words, and finally we will show how some string attractor based complexities can be used on finite words to get some new interesting characterization. So let's start right away. So here we have the definition of a string attractor, which was first introduced by Kempe and Prezza in Stock 2018. And basically a string attractor gamma of a finite word W is a set of small gamma positions such that every distinct factor of W has at least an occurrence crossing a position in gamma. So if this is our finite word W, and these are the positions marked in the set gamma, in order to be a string attractor, for each factor that does not cross a string attractor position, there must be at least an occurrence with that. So here we have an example. So let us consider this word W and the set gamma, which consists in the positions highlighted in W. In order to see if gamma is a string attractor, we have to list all factors with occurrences not crossing a position in gamma. So starting from those of length 1, we have D, C, A, B, D and A we already listed. Then we have these two factors of length 2, which are DC and BA. So in order to check if it is a string attractor, we can see that all these factors of length 1 are covered by the A by this position, then we have the B, C, and D. While for DC, we have an occurrence here, position 11, which are covered by this by 11. And the factor BA also occurs starting at position 4. So all the elements of this list are covered by string attractors. So this by this set gamma, so gamma is a string attractor. However, we want to point out that also the set gamma star is a string attractor too, which is the same as gamma, but without the 1. And this can be checked because all the factors that crosses position 1 and just position 1 among the positions in the string attractors are also covered by position 6. So we can say that this set is a string attractor. Not that the size of this string attractor gamma star is minimum, since any string attractor must verify that its size is at least the size of the alphabet used. And we denote by gamma star the size, small gamma star, the size of a string attractor of minimum size. And it has been proved in the same work by Kempe and Prezza that computing the size gamma star for a word W is an NP complete problem. So as I mentioned earlier, the notion of string attractor was defined in data compression. And in fact, this is mostly due because string attractors can be considered as a unifying framework for different compression schemes, which are based on repetitions. And in fact, they proved that for these sizes of compression schemes applied to a word, these are sort of implicitly induce a string attractor. So these compression schemes, these compressors are the so-called dictionary-based compressors, and basically these exploit repetitions in order to compress and index data. And these are very efficient on a highly repetitive data sets, such as DNA sequences or astronomical observation. And the relationships among compression schemes and repetitiveness measures are of current interest. And there is this very well written recent survey by Gonzalo Navarro, which can be used to study the current state of art. Also in recent works, Koshimaka and others in Latin 2020, and also a work that has to appear in the edition of this year of Latin, they investigated the so-called delta measure of a finite world, which consists in the maximum ratio of the number of distinct factors of length k over k. And in this case, we denote with a big F of W the number of distinct factors in our finite world. So these delta measures actually represent a natural lower bound for the size of a string attractor. In fact, this is can be intuitively understood because for each position of J of a string attractor, this position can be crossed by at most k distinct factors of length k. But also, in order to highlight the deep relationship between string attractors and repetitions, we have this other lower bound with respect to the length of the longest repeated factor in a word. So now we'll talk about some combinatorial properties of string attractors, and in particular, I will focus on how classical combinatorial operations applied on finite words can affect the size of a small string attractor. And most of the results come from the paper A Combinatorial View on the String Attractor, which is a joint work with Sabrina Mantaci, Antonio Restivo, Giovanna Rosone, and Mariella Shortino. So let's start by considering the reverse of a word. So in this case, it's sort of easy to see that the size of a small string attractor for a word is the same as of its reverse. And this intuitively can be observed. In fact, basically for the reverse, given a string attractor for a word W, we can pick as position in the reverse the symmetrical with respect to the center of the word. And this will lead to the fact that all the factors in the reverse that are not covered in the reverse of the word, they will covered somewhere else. So what about the concatenation? In this case, also we have an intuitive upper bound. So given two finite words U and V, and the respective size of their smallest string attractor, the size of the smallest string attractor for the concatenation is the sum of gamma star of U and gamma star of V plus 1. This is due to the fact that if we keep the relative position with respect to the concatenations, then we are certain to cover all the factors within U and V, but we add just one position in order to cover those in between in the concatenation. So what about the powers of a word? In this case, we have the following proposition. So basically, the smallest string attractor size for any power is less or equal than the size of the smallest string attractor W plus 1, while the size of any power must be equal to the size of the smallest string attractor of a square. Just to give you a hint on how we prove that. So for the first, basically, we showed that with respect to the root in any power, we can keep the same positions in the first occurrence, and just in order to cover those factors that cross one or more, two or more consecutive occurrences of W, we just pick a position in the concatenation. Well, for the second case, in order to see how it relates with how the size of the square and any other power is related, we proved that from a small string attractor for from any string attractor of a square, we can deduce a string attractor of the same size in any power, and vice versa. So in Latin 2020, Cochumac and others posed the question whether or not this measure gamma star of the small string attractor is monotonic. So in other terms, if gamma star of W is always less or equal than W concatenated with U for all words W and U. And actually, in attempting to solve this problem, we came up with the solution that no, it is not monotone. And in fact, we have this very short example that actually would be useful. So if we consider this word W, we can see that this has a small string attractor of size 3. In fact, this is a suitable small string attractor, and you can notice that the factors in different colors have only one occurrence, which forces us to cover these factors with appositions. So in this case, we have these 3 colors, so we need at least 3 string attractors. However, if we append B, then we can see that the factors ABB and AAB actually overlap in between positions 7 and 8. So by keeping in position 7, we can actually avoid to store position 2 as a string attractor, and therefore the size of our smaller string attractor has decreased. So we wonder if there were some cases where actually the monotonicity holds. And we wonder if this actually holds when we consider the power of a word. But also, not only in this case, we come out with the same solution, that is that the monotonicity does not hold for a power of a word, but actually we prove a stronger result. That is that for each t greater than 0, there exists an alphabet, sigma of t, and a word wt, such that this difference is between the small string attractor on the root and the power of this wt is greater than t for each n greater or equal than 2. Just to give you an hint on the proof, we have considered a word w, and we have built in a way such that there are certain factors that occur exactly once in w. However, when we are forced to place a string attractor position in correspondence of each of these factors. However, when we consider a square or any other power, all these factors actually overlap in the concatenation. So we can use just string attractor position in order to cover exactly these factors. And actually, using the same example, we obtained a similar results for the conjugate words. In fact, we proved that for each t there exists an alphabet and a word, which can be decomposed into subwords u and v, such that small string attractor for uv minus the small string attractor for vu is greater than this t. And the idea is basically the similar. So basically, we remove the prefix and append at the end of u in a way that these factors occur in the concatenation. So here we have a sort of an open problem both for the power and the conjugacy. That is that we have for each t, we need to expand our alphabet in order to get this gap. So we wonder if for a fixed alphabet, actually this gap can also be bounded. Now I will present some results on infinite words. This will appear later this year in paper, String Attractor and the Infinite Words, which will appear later in 2022. And it is a joint work with Antonio Restivo and Marinella Shortino. So let's start by considering a class of infinite words, which are characteristic Sturmian words. So many of you probably are aware of what characteristic Sturmian words are. And basically, it is known that given a directed sequence, we can inductively define an infinite sequence of words, and each of these finite sequences is called standard Sturmian words. While the limit, if we consider a limit for it tends to infinity of the term of this sequence, this is the so-called characteristic Sturmian words. These words have a lot of properties, and very well known is the Fibonacci word, which is obtained by considering the directive sequence of just once. And basically, in our previous work, we actually proved that for each standard Sturmian word with length greater or equal than 2, if we consider eta as the length of the longest palindromic proper prefix of the standard Sturmian words without considering the last two symbols, then we can find a suitable string attractor for this word S, which is related which consists in two consecutive positions, and these positions are related to the size eta. So, for example, for the Fibonacci word, we have in the first case we have that shortest palindromic prefix of ABA is A, and actually we pick as a suitable string attractor eta plus 1 and eta plus 2. Same goes for S4, where the longest palindromic prefix is ABA, so we pick AB, and so on and so on. So now we actually we have considered finite words. So why are we talking about infinite words? Well, actually, it's not that easy to extend the definition of a string attractor to infinite words. And this can be observed because, for instance, given an unidirectional infinite word X, we may find at a certain point a certain factor, and we may wonder, okay, we may try to pick this position for our string attractor. However, later in the word, we may find the same factor plus a new one that we have never seen before. So in order to cover both, it may be convenient to actually replace the one we picked before the new one. But this can actually occur infinite many often, and therefore it is not actually possible for an infinite word to locate the positions of a small string attractor. On the other hand, we've seen how for standard Sturmian words, which can be seen as sequences of prefixes of characteristic Sturmian words, we have defined a small string attractor. So we think that the definition given by Scheffer and Schaldi can be, it is a suitable notion of string attractor for infinite word. That is the string attractor profile function, defined as for every n as this is the size of the smallest string attractor for a prefix of length n. Since we want to relate this this function with other function related to repetitiveness in infinite words. In the next two slides, I will present briefly some of the notions that we need and the notation that we used. So let X be an infinite word. The factor complexity function P of X denotes for each m the size, the number of distinct factors of length m that occurs in the word. With A of X, we denote the appearance function, which for each length of m it returns the length of the shortest prefix of x, which contains all factors of length m. So, for instance, in this case, it is ax of m because these three factors already occurred before. So then we consider the recurrence of a word, and a word, infinite word x is called recurrent if every factor of x occurs infinitely often. So for instance, if here we have our infinite word x, we will expect that every factor will appear infinitely many times in the word. If there exists a function Rx of m, which is called the recurrence function, such that every factor of x of length Rx of m contains at least an occurrence of each factor of x of length m, then the word x is called uniformly recurrent. Further, if Rx of m is linear, then x is called linearly recurrent. Now we will express a relationship between the string attractor profile function and the factor complexity. In fact, this theorem that can be deduced is that for all given an infinite word, for all m greater than 0, one has that the factor complexity function over m is less or equal than m times the string attractor profile function on the Prince function of m. So, and this is it follows from the observation that if you consider this window, and if you consider a string attractor for the prefix of this length, this comes basically from the lower bound that we have defined with respect to delta. But however, a corollary that we can deduce from this theorem is that if there exists constant k such that the string attractor profile function is always bounded by this k for each n greater than 0, then the factor complexity function is always upper bounded by m times k. In other words, if the string attractor profile function is bounded by a constant, then x has at most linear factor complexity. So here we have considered another issue. So basically, look, Schaeffer and Jeffrey Shalit proved that saying that word x is linearly recurrent implies that the string attractor profile function is bounded by a constant. This sort of confirms what we obtained in the previous result. In fact, saying that the word is linearly recurrent actually implies that both we have recurrence function that is linear, but also the factor complexity must be linear. However, not all infinite words with a constant bound on a function, on the string attractor profile function, are linearly recurrent. In fact, in this work, we proved the same result for all Sturmian words, but every Sturmian word is uniformly recurrent, and not all are linearly recurrent. So here we have an open question, which basically wonder if we can lighten up this the condition posed by Schaeffer and Shalit. So let x be a uniformly recurrent word with linear factor complexity. Can we say that the string attractor profile function is bounded by a constant value? And here we show a table with some results with respect to the string attractor profile function. So here one of the results that we obtain is that for all characteristic Sturmian words, for which we know that all of these are uniformly recurrent, and also with linear factor complexity, we have found a string attractor of size 2 for our prefixes. And Schaeffer and Shalit actually for the period doubling to a Morse word and a sequence of the characteristic sequence of the powers of 2. They proved this results, more in particular, they proved they were studying string attractors for automatic sequences, and they showed that either they have either they have a string attractor profile function bounded by a constant, or the growth for the string attractor profile function is logarithmically grows logarithmically with respect to the size n of the prefix considered. So, given this this scenario, we wonder if we can actually say that these two conditions must be verified in order to get this bounded by constant string attractor profile function. One last thing on this part is that we actually wanted to we considered also other words with string attractor profile function bounded by a constant. In fact, if X is ultimately periodic, which didn't fall in any of the cases before, the string attractor profile function is also bounded by a constant. In fact, this comes from the properties that we have mentioned before with respect to the concatenation and with respect to the power of a word. However, we also got this proposition, that is, if a string attractor profile function is bounded by a constant, then either X is ultimately periodic or omega power 3, where with omega power 3, we mean that for each factor u of X, there exists k such that u to the k is not a factor of X. So clearly, if X is ultimately periodic, then with the previous proposition, we know that the bound holds. So let us suppose that the word is aperiodic and not omega power 3. Then, in this case, we will have an infinite amount of these rounds of powers of u, which each of them have a different context on the left or on the right, which leads to the fact that for each of these powers, we must place at least a string attractor position. So the string attractor profile function cannot be bounded. So now in this part, we will consider some new string attractor-based complexities. So let us start by showing why we started wondering if we could say something more by using string attractors. So here we have 3 examples of infinite words which emit string attractors with bounded sides. On top, we have the periodic word AB to the omega, which is obtained by concatenating infinite times the word AB. Then we have the Fibonacci word, and then the period doubling. For all this word, we can easily prove that the string attractor profile function is punctually the same for all n greater than 0. However, it is clear that we are not talking about the same string, the same word, and in fact, one can actually notice that there are some properties of some string attractors that can be considered. For instance, for AB to the omega, the first 2 positions represent a suitable string attractor for each prefix of the word. For the Fibonacci word, as any other characteristic Sturmian words, we prove that we can find a string attractor with 2 consecutive positions, but we have to move this position as the length of the prefix grows. While for the period doubling, Schaeffer and Shalit proved that it can be built an automata which returns these 2 positions of the string attractor, but the distance between these 2 positions grows as the length of the prefix considered. So here we introduced two new notions related to string attractors. And so instead of just focusing on the size of the string attractor, we have considered other structural properties. So let us consider G as the set of all suitable string attractors for a given finite word W. So we define span of W as the minimum difference between the last element and the first element of a suitable string attractor for W. While with leftmost string attractor, we refer to any string attractor that verifies that as the minimum last position. So to give an example, here we have this word W, and in this case we can see that the span of W is 2. In fact, here we have a string attractor which consists of 3 consecutive positions, C, A, B. So this is also a smallest string attractor because we have 3 symbols. In this case, we have the maximum, which its maximum element, which is 6, minus its first element, which is 4. In this case, this is the span, and it can't be less than that. On the other hand, we have that this other string attractor consisting in position 1, 2, and 4 is one that represents a leftmost string attractor. So the leftmost of W is 4. We want to highlight that actually for these examples, and so we guess for many infinite others, we had to use 2 different string attractors to get these 2 measures on W. So we couldn't find, in this case, we couldn't find that example that was suitable for both the span and the leftmost. However, it is still an open question if we had to consider the set G of all suitable string attractors, or just like in this case, we can actually find always a smallest string attractor, which returns us, which can be used to retrieve the span and the leftmost string attractor. So analogously to the string attractor profile function, we define the span and leftmost complexity for infinite words as the span and the leftmost for each n of the prefix of length n of an infinite word x. So here we have our first proposition, which relates all these measures among them. And we have that the string attractor profile function for each n minus 1 is less or equal than the span complexity, which is less or equal than the leftmost complexity. Just to give you a hint of the idea, if we consider a certain context n, and the last position, which of the leftmost string attractor, you can clearly see that the span of this string attractor of size L would be, of course, greater or equal than the actual span complexity up to that length. And as we have seen before, basically, how many string attractor positions can be in a string attractor with a certain span? At most, if span plus 1, so when the string attractor is completely dense. So every position between the first and the last is actually a string attractor position. So we started to, as we have seen in the first example, we can derive this characterization for ultimately periodic words. So let us consider X as an infinite word. We have that X is ultimately periodic if and only if there exists K, such that leftmost complexity is always upper bounded by this K for infinitely many M. So, so on one direction, it's sort of, let's say, trivial, because we can always derive string attractor in the first positions, as we have seen in the proof for the powers. Well, on the other hand, it can be proved because if the string at the leftmost is upper bounded by a constant, then how many factors can we actually have? Of any length, and most actually k. So since the factor complexity is bounded by constant, then this is actually the definition of ultimately periodic word. So we'll consider now what will happen if the span complexity is bounded by a constant. So given an infinite word x, if there exists a constant k such that the span is less or equal than k for infinitely many n, then the infinite word x either is recurrent or ultimately periodic. So if x is ultimately periodic, we have seen that x is a k such that the leftmost complexity is bounded by this k, and since the leftmost complexity is an upper bound for the span, we have proved for ultimately periodic word. So on the other hand, if x is aperiodic, then that means that for each k greater than 0, there exists n0 such that the leftmost complexity is greater than k for all n greater than this value n0. So to prove that it must be recurrent, let us suppose that it's not recurrent, which means that there exists at least a factor u of x that occurs only once. This means that when we find this factor u, we are forced to string attractor positions within the range where u occurs. But since we cannot bound the leftmost complexity, then the span of this string attractor cannot be bounded by any constant. However, we can also obtain a stronger result. In fact, if the span complexity of an infinite word is bounded by a constant, we can deduce the following lemma, which refers actually to finite word. So given a finite word w, for all n, it holds that the number of distinct factors of length n is less or equal than n plus span of w. In fact, the idea is similar to the bounded leftmost. However, in this case, we have that if we have a certain span k, then how many factors of length n can we have? At most n plus k distinct factors. So this relationship can be actually used to prove the result, a new characterization for Sturmian words. In fact, it is known that an infinite word is Sturmian if and only if the factor complexity is m plus 1 for m. So we were able to prove that given an infinite periodic word x, x is Sturmian if and only if the span is equal to 1 for infinitely many n. So to prove from one direction, the easiest direction comes from the fact that it is known that a word, if word x is aperiodic, then the factor complexity is at least m plus 1 for m, while having a span equal to 1 for infinitely many n, and given the fact that the factor complexity is a monotone function, then the factor complexity is also upper bounded by m plus 1. So lower bound and upper bound match, and therefore the factor complexity is m plus 1 and x must be Sturmian. For the other direction, so being Sturmian implies that By using combinatorial arguments, we can prove that exists a certain n0 such that every characteristic Sturmian word S prime admits a string attractor with span 1. Every Sturmian word, like every other aperiodic and recurrent word, has an infinite number of right special factors as prefixes. And where a right special factor is a factor u, and I mean, it is called right special if there exist two symbols A and B from the alphabet, such that both UA and UB are factors of X. In the work of lateral algebraic combinatorics on words, it has been proved that for every right special factor U of a Sturmian word, there exists a characteristic Sturmian word S prime that has the reverse of that right special factor as prefix. So, for instance, if this is a generic Sturmian word, and this is one of the prefixes in this right special, this means that we have a characteristic Sturmian word with the reverse as prefix. But we have proved that for characteristic Sturmian words, we always have a string attractor with two consecutive positions. And given the property with respect to the reverse, this holds also for all these prefixes which are of infinite numbers. In order to present our last result, I need to show this result on finite words when morphism is applied on finite words. In fact, let's consider morphism phi. Then there exists a constant k, which depends only from phi, such that for every word w, this upper bounds on the string attractor, on the span, on the leftmost string attractor holds. In particular, I want to highlight the result on the span. So the span of the image of word w is k times the span on the word. And intuitively, this comes from the observation that for any given string attractor of w, we can retrieve one suitable for phi of w by picking the border of the projection of the symbols, plus some extra symbols in order to cover those factors that occur only within the images of the symbols. So we'll use this to provide a new characterization for quasi-Sturmian words, where an infinite word X is quasi-Sturmian if there exist two integers n0 and k, such that the factor complexity function is always n plus k for all n greater than n0. So Sen provided this proved that this factorization holds for all quasi-Sturmian words. That is that basically any quasi-Sturmian words can be decomposed as a prefix, which is any finite word, and a suffix, which is actually the image of a morphism phi that does not lead to a periodic word applied over any Sturmian word. So we were able to obtain the following characterization. So we prove that an infinite aperiodic word X is quasi-Sturmian if and only if there exists a suffix Y of X and an integer K, such that the span of this suffix is always less or equal than K for infinitely many n. So in order to get the results, we have considered that by using the characterization of the factorization of Cosine, we can actually exclude the prefix u and just consider as y a suffix y, actually phi of s. And in fact, recall that for every Sturmian s, it holds that the span is equal to 1 for infinitely many n. And also that there exists k that depends from phi, such that the span of the image over W is less or equal than the span, the k times the span on W for every W. So it follows that for infinitely many n, we will have that span of phi of s length n is less or equal than k times the span of s, that is equal k times 1, and so the thesis follows. Also, of course, the other direction comes from the observation that if we have a bounded span, then the factor complexity is at most n plus k. So, in conclusions, we have here introduced the notion of string attractor from a combinatorial perspective, and we have seen how an NP-complete problem in general it can be solved for infinite families of words by using some combinatorial arguments. And also we've seen how we can use this notion to obtain new characterizations of words. So here we have some open questions left. So are there other structural properties of string attractors that can be used to characterize infinite words? So can be different from the leftmost or the span complexity, but it can be also find new characterization with respect to how this function grows, for instance. And another question that we have left that it refers to finite words is if, in general, for every finite word W, is there a set of string attractors that uniquely characterize a word W, which allows you to recover the word W up to, of course, a permutation of the alphabet. So that was everything. Thanks for your attention. And if you have any question, I would be glad to answer.
Thank you. Thank you very much. Does anyone have any questions?
Narada, I think Marie-Pierre has one. She raised
sorry.
her hand, yes.
Yes, thank you. I'm Marie-Pierre.
Yes, thank you. I have a question. So you said that it's NP-complete to compute gamma star for a random word. And then you have families for words where you can compute SX. Do you have formula for these words? Or it is computable in polynomial time for SX of n is computable in polynomial time? And for instance, if you have an automatic sequence, SX of n computable in polynomial time? Or you have
well, in the work of Schaffer and actually they showed how it is possible to build an automata which returns these positions. So yes, for instance, for automatic sequences, this is possible.
So you can compute SX of n, and you also have formulas for SX of n?
Yes, because you can deduce the positions of the string attractors that are used, basically. So you can also deduce both the sides and where these are actually located.
Okay, thank you.
You're welcome.
Any other questions? Like high complexity words, like things like, I don't know, De Bruyne words or?
Yeah, so since the delta measure is a lower bound, right? So, which is the number of distinct factors of length k over k, the maximum of this ratio. And for the Brewing words, if you consider a linearization of the Brewing words, these are actually sigma to the k over k, where k is the degree of the Brewing word, which can be considered as n over log n. And also there's been proved that for any word we have the Lempel-Ziv of any word is sort of the same order, let's say, so n over log n. So it is very roughly lower and upper bound, but yeah, it is supposed to be something around n over log n.
Gotcha. Does anyone else have a question? All right. Well, thank you so much, Giuseppe.
Okay.